Hey folks, I have some rotational kinematic examples for you. We'll see how far we get. I got 5 total. Maybe we'll do them all in this video. Maybe we'll have to do 2 videos. Uh, a quick reminder, in the previous video, or in class, we talked about the equations for rotational kinematics. That's these folks on the left here. And we also talked about how to translate from a rotational or quantity, such as theta or omega, to its associated linear quantity if you're like walking in a circle. Okay. We also talked about briefly radial acceleration in terms of tangential velocity or um, rotational velocity. So we're going to be using probably all those equations in these examples. So hopefully you have them handy and you're ready to look at them. All right. So I have 5 examples. The first one, very straightforward. Let's say we have a clock. Okay. So for a clock, here's what I want to do. I want to find the angular velocity of the second hand, and then the minute hand, and then the hour hand. And we're going to do those in radians per second. Okay. So let's start with the second hand. Omega s is equal to delta theta over t. Okay. And there's a lot of ways you could do this. I'm going to look at when each of these hands does one full lap, which is 2 pi radians. Okay. Well, for the second hand, that takes 60 seconds. And you can reduce this to pi over 30. And that would be radians per second. Okay. The minute hand does 2 pi radians in how much time? Well, it takes an hour for the minute hand to go around once, which is 3,600 seconds. And that would be pi over 1,800 radians per second if I reduce that. And then we have the hour hand. I'll do that right here. For the hour hand, it does 2 pi. How long does it take the hour hand to go around? Nope, it's not 24 hours, it's 12 hours. So we got to take 12 times 3,600. And you could reduce this a little bit. You could say pi over, let's see, 6 times 36 would be, I don't know, 6 times 36. That would be 216 and then 2 zeros. So there you go. And that would be radians per second. So by the way, the hour hand moves incredibly slow. If you're watching an hour hand, it's going to look like it goes incredibly slow. So that's our first example, just kind of talking about angular velocity and how quickly something is spinning. All right, our second example, well, now we get a little more mathy on you. Let's say I give you the following problem. Let's say something is spinning and its starting angular velocity, so that's omega naught, is 10 revolutions per second. Okay, and let's say it has an angular acceleration of 3 radians per second squared. Now, hopefully right away you see an issue, right? Or you hear an issue in my voice. And then let's say this happens for 2 seconds, okay? Here's what I would like to figure out. I would like to figure out theta as a function of time, okay? And then what is the angular displacement after that 2 seconds, okay? Now, in this problem, I did not give you a theta naught. So if that's the case, we're just going to say the theta at 0 is just 0. We're going to start at the start line, okay? The one issue you hopefully heard is that the omega naught is in revs per second, and I'm going to rewrite that over here. It's 10 revs per second. We need radians per second. So there's 2 pi radians in 1 rev. Okay, so the revs drop out and you get 20 pi is our starting angular velocity. I'm just going to leave it as 20 pi. You don't need to put that in a calculator. Okay, and we can leave all these answers in terms of pi and such. Okay, so this is a constant angular acceleration question, so I'm allowed to use all my equations of motion with constant acceleration, and the one I'm going to pick is theta as a function of time equals theta naught plus omega naught t plus 1/2 alpha t squared. Okay, and basically we have all this stuff, right? Theta is 0 plus omega naught is 20 pi times t plus 1/2 Alpha is 3, and then we have our t squared. So that is alpha or theta as a function of time, okay? And then to get delta theta, well, since theta naught is 0, delta theta simply is theta, okay? So theta at 2 seconds, well, you just plug in your 2 for time there and there. And so the first term would be 4 pi, okay? And the other term would be, oh, I forgot something. Oh my gosh. This is up here. This is not 2 pi. It's 20 pi. Sorry about that. Hopefully you caught that for me. And so this should be 40 pi. Okay, there we go. And then plus 1/2 of 3 times 2 squared. So that's 3 times 4 is 12. Half of that is 6. So the angular displacement after 2 seconds would be 40 pi plus 6 radians. And if you wanted to, you could plug in a calculator and get an actual decimal answer if you want. But for this purposes of this video, that's fine. Just leave it like that. Okay. So there's you go. There's your answers. Okay. For example 3. Okay. Example 3, let's say I give you the following function. I give you theta as a function of time. So this is something spinning, and theta as a function of time is 3 plus 7t minus 4t squared plus 2t cubed radians. Okay? And what I would like to determine is what is the angular velocity as a function of time. What is the angular acceleration as a function of time? And what is the average omega from 0 to 2 seconds? Okay, so what are these three things? Well, first of all, since we have a t cubed, okay, this is not going to be a constant alpha equation. Okay, so our equations of motion that rely on constant alpha, we can't use them here. Okay, but I do know the 4 equations that always work are omega is d theta dt. I know that alpha is d omega dt. I know that average omega is change in theta over time. And I know that average acceleration or angular acceleration is change in omega over time. Those 4 always work. That's what's going to get us through here. Okay. So if I want to find omega as a function of time, I simply take the derivative of this. So omega as a function of time is d theta dt. The first term will be the derivative of 3 is 0. The derivative of 7t is 7. The derivative, we got minus. The derivative of 4t squared is 8t. And I have a plus. And the derivative of 2t cubed is 6t squared. So that is omega as a function of time. Alpha as a function of time is d omega dt. So I'm going to do the derivative of that. The derivative of 7 is 0. The derivative of negative 8t is negative 8. And the derivative of 6t squared is 12t. Okay, so there are omega and alpha as functions of time. Finally, average angular velocity between 0 and 2 seconds. So for that, I'm going to have to use this equation. So I need to know what theta at 0 is. So all I do is I plug in 0 into our theta equation. And I get 3 plus 0 minus 0 plus 0, which is 3. Okay, and then I have to plug in theta at 2 seconds. Now that I got to do a little work for. We got 3 plus 7 times 2 minus 4 times 2 squared plus 2 times 2 cubed. And this equals, let's see, 3 plus 14 minus 4 times 4 is 16, and then plus, well, that's 16. So these last two things cancel, and I get 17. Okay, so now we got a real easy problem. The average omega is delta theta over t. My theta went from 3 to 17, so that's a change of 14, and my time was 2 seconds, and my average omega is 7 radians per second. All right. All right, so we got through 3 examples there. I've got 2 more for you in the next video, so I hope you found that helpful, and thank you very much.